Okay, I'd like to welcome everyone here tonight. Thanks for coming to listen to this seminar from the Institute of Energy Efficiency. It's really my pleasure to introduce Dr. Charles Forsberg, who's a director and principal investigator for Department of DOE's Integrated Research Project. He's a professor at MIT, teaching fuel cycle and nuclear chemical engineering courses, and was a corporate fellow at the Oak Ridge National Labs, and has a whole host of honors along that. He's a fascinating conversationalist. We had a really good discussion this afternoon on a whole host of topics related to energy, and I'm really looking forward to your talk.
Well, thank you. I want to discuss heat storage and the electric grid. Very much of an emphasis on the fact that if you're going to have energy storage, you have to be able to afford it, which is why we're talking about heat storage. I realize it doesn't have the sexy appeal of lithium-ion batteries, but it might economically be deployed on a much larger scale. Now I'm going to discuss integrating nuclear renewables in a low-carbon grid. I'm going to cover economics, electricity markets, and then heat storage. The starting point, which I think is really important in any discussion of energy, is that energy is 8% of the world's gross national product. You know, if something's 1% and you double the cost, we can do that. It's affordable, it's not a big impact. If it's 8%, major increases in energy cost imply major decreases in standards of living. It also implies serious problems in much of the developing world where there are billions of people who have shortages of energy. In short, economics is central. And the viability of getting off of fossil fuels depends upon an economic replacement. If you end up tripling the cost of energy if the cost of going to a low-carbon world is 3 times larger than today's energy cost, I would suggest you're not going to have a low-carbon world. We'll live with the fossil fuels. We'll keep burning them because the alternative is too expensive. The impact on society, the impact on standard of living is too great. And so the viability of getting off of carbon is doing it in an affordable way. Well, let's take a look at what's changing in energy markets. My first observation is there's been no change in energy policy for 300,000 years. Throw a little more carbon on the fire. Now, I recognize that this cooking fire looks a little bit different than the gas turbine, but economically, they're almost identical machines, because in both cases, the cost of that cooking fire, you know, the stones, the time to collect it, and the cost of that gas turbine was a small part of the cost of energy. If that's not where the money is. The money, the effort, the resources, the labor, the man-hours is collecting the firewood or the natural gas and bringing it to the fire. Now, what's the practical implication? If I run this cooking fire and I turn it off for a couple of hours, it doesn't cost me a lot of money because I didn't spend a lot of money collecting the stone. If I turn off the gas turbine for a couple of hours, it doesn't cost me a lot of money because that's not where the money is. I can run these technologies at part load with very small impact on the total cost of energy. Who cares if the gas turbine runs half the time? That's not where the money is. The money is in the natural gas. So it's easy to have variable electric output. It doesn't cost as much. Now let's take a look at nuclear, wind, and solar. These are high capital cost, low operating cost technologies. The operating cost, you know, is in the noise level. What's the implication? You have to run these at full capacity for economic energy production. If you run any of these technologies at half load, you've doubled the price of energy. That's an extraordinary economic impact. So if you want economic systems that are low carbon, you have to figure out how to run them at reasonably close to full capacity. Now, having discussed what the major transition is from low capital cost to high capital cost, high operating to low operating, let's take a look at the market impacts of adding wind or solar. This happens to be the solar impacts on Southern California. This red curve is the wholesale price of electricity in California in 2012 over a period of 1 day. The blue curve is the 2017 price of electricity in Southern California over the same day. And what you notice is the price of electricity went negative in the middle of the day. That was because people built a lot of solar systems. Now, what the market is telling us is the value of solar energy in the middle of the day is 0. And what that means in a practical implication is I don't care how cheap your solar cell is, 0 times a lot of kilowatt hours, still 0. You're out of luck. I should mention in this specific example, the negative prices come from gas turbines. Oddly enough, the gas turbines start revving up here, and I want them to stay online at minimum load, so when the sun goes down and the price of electricity goes up and the price and the demand goes up, they can rev up 16,000 megawatts in about 3 hours. But to do that ramp rate, they have to start early in the day and be hot and ready. And so the gas turbine guys pay the grid dollars per megawatt hour to take their electricity so that at 5 o'clock in the afternoon, they can push the accelerator, ramp up, and get lots of money in revenue. Welcome to the market of the future. Wind does the same things. This happens to be the Great Plains. It's a similar story. Now, what we need is storage to match production with demand, but what kind of storage? And for those of you who are thermodynamicists, well, the answer is obvious. There are only two kinds of storage. You're either storing heat or you're storing work, which we often call electricity. And of course, the electricity options are quite varied. So let's take a look at these two options, storing heat versus work. Now, heat storage is cheaper than electricity storage. There was recently a review paper of electricity storage papers, electricity storage technologies, pumped hydro, batteries, about 13 or 14 technologies. An extraordinarily depressing paper, if you read it, because it estimated electricity storage costs, battery pump storage, so forth, at about $340 per kilowatt hour at the terawatt grid deployment scale. And the bottom line on that is, those cost numbers imply that you're more than doubling the price of electricity if you put storage into the system. Really depressing story. And the reasons why, let me use an example, is a lithium-ion battery. The problem with a lithium-ion battery is it's got 3 really expensive components: lithium, cobalt, and fluoride or fluorine ion in the hydrocarbon. And when you start with expensive raw materials, you end up with an expensive final product. Simple as that. If you want a cheap final product, you got to have cheap starting ingredients. Now, the DOE battery goal is $150 per kilowatt hour. That's the battery only. It doubles if you add all the electronics, AC, DC, concrete foundation, and the rest. The Department of Energy storage goal for thermal energy storage is $15 a kilowatt hour, a clean factor of 10 less. And so a lot of studies have come to the obvious conclusion that although heat storage is dull, boring, monotonous, if economics is important, you better start paying attention. Now, let's take a look a little further in heat storage. They have 3 separately sized components. You got to put heat into the system. In most cases, that's really cheap. You got to store the heat in some form, and then you have to convert, if you're making electricity, you have to convert the heat back to electricity, which tends to be an expensive activity. Now, if you start looking at that economics, heat storage economics favors oversizing the heat to electricity storage conversion system. And in most cases, in a nuclear plant, that's the steam to electricity system. However, the incremental cost of oversizing that steam turbine, the turbine hall, is a fraction of the standalone cost of the power conversion system as a whole. So what we're talking about is we have a reactor, for example, or a solar power tower, a heat storage system, and then we have the power conversion system that converts the heat back to electricity. And instead of buying maybe a 100 megawatt or a 1,000 megawatt or a 10 megawatt turbine hall, we're going to make it maybe 20, 30% larger to convert heat that's been in storage back to electricity, realizing that the incremental cost of that small addition of capacity is very, very low relative to the cost, for example, of a gas turbine. Well, this is all about money. Well, as you may have noticed here, I've gone through a lot of talk and discussions, and I haven't actually mentioned any heat storage technology, so let's take a look at that. There are 6 classes of them, and I'm going to very quickly go through a couple of these as examples of heat storage technologies to match match low carbon energy production with demand. One observation here. Nuclear and solar thermal use similar storage systems. In many cases, they're absolutely identical. In some cases, they're different, and that's because you use the same coolants, steam, salt, future salt, sodium, and you use the same power cycles. So, for giving it NREL, I would emphasize more the solar than the nuclear, but that's a fine point. Well, let's take a look at the first option: electricity to stored heat to the user. And I'm going to briefly mention Firebrick resistance heated energy storage. This is the simplest technology. There's a paper you can read that I wrote if you have an interest in it. Now, what's Firebrick resistance heated energy storage? The idea is very simple. Buy electricity when electricity prices are less than the cost of fossil fuels, such as natural gas. Negative priced electricity is definitely cost less than natural gas. Electrically heat an insulated mass of fire bricks to very high temperatures, ultimately 1600 C. Blow air through the channels in the hot fire brick to deliver hot air out for 2 applications: industrial heat to furnaces and kilns as a partial substitute to natural gas, or peak electricity in a boiler or gas turbine. Now, of course, this is an old technology. Firebrick's been around since the Hittites. We do have to do electrically heating. That's a modern technology, only a century old, but a little old, little new. Here's the schematic of it. Again, buy electricity when the prices are low. There are 2 criteria to buy electricity when you heat Firebrick. First, buy below the industrial price of the fossil fuel. And if the price varies, you want to buy most of the electricity when the prices are lowest. So although you may have 8 hours of low-priced electricity, if there's 4 hours with really cheap electricity, you want to buy it then. Buy low, sell high. Discharge fires when you have higher electricity or gas prices. And what we're talking about is a partial replacement for natural gas. So we heat Firebrick, run cold air through it to produce hot air for industrial furnaces or gas turbines, and it's a partial substitute for natural gas. And of course, we can adjust the temperature by adding cold air or natural gas, as the case may be. What's the current status of technology? The Chinese use electric heat storage for large apartment complexes. They have an 8-hour discount rate at night for electricity production, for electricity use for home heating to reduce air pollution. And they use these units for apartment complexes that have several 100,000 square meters of space. These are absolutely incredibly big apartment complexes. And it's to replace coal boilers that are sitting right next to the apartment complexes. In the middle of the night, they heat up a bunch of Firebrick. This happens to be individual units. These units are used to heat hot water to 85 C, which is circulated through the apartment complexes. And so you have hot air circulation between fires and hot water. The goal for any factory fabricated system is to be substantially under $15 a kilowatt hour, and these systems are in fact below that cost. The limit is on the electrical heating system at about 850 Celsius. Now, if you can develop fires to higher temperatures, you can use it anywhere hot air is used as a substitute. That's industrial boilers and furnaces, utility boilers, including the conventional coal boilers, gas turbines, and something called a nuclear Air-Brayton power cycle, which is a very advanced power cycle that takes advantage of the unique characteristics of fires. And of course, what we are is we are a bottom dweller. Here's our price curve. If you install fires, this is what you do is you buy it when it's cheap. It's a bottom dweller for the industrial market or gas turbines. Well, let's take a look at some of the other technologies for variable heat output from a nuclear reactor or solar plant and see where they stand in various technologies. First, I'm going to mention one item about light water reactors because it turns out a lot of people are not aware of this. In countries such as in France, Light water reactors vary power levels from 50 to 100%, depending upon demand, and they've been doing it for 40 years. I mention that because every so often I get a question from the audience, but light water reactors only do base load, and I said, well, that's in the United States because of our economic conditions. You can run a light water reactor up and down like a yo-yo. It's not very economic, but if the market makes that the preferred mode, you can do it. So I just want to, that's a clarification, but I keep having this, I keep reading these papers where they talk about, nuclear can only do base load, and my answer is, guys, you obviously haven't read anything in the literature for at least 45 years. By the way, you may not be aware of this, but did you know that submarines go up and down all the time in power levels? Full power, full reverse. Carriers do the same thing. So there's point of observation. Well, our first option for heat storage is between the power cycle and the generating plant. And this one technology that's used today is you have a heat generating technology. It could be solar, could be nuclear. You produce a hot fluid. That hot fluid goes to a hot storage tank to get a hot fluid, or to the power cycle to produce electricity. And you have the cold fluid coming back, could be salt, it could be a variety of other fluids. And if you have cold fluid, it can go into storage, or it can go back to the heat generating technology, be it a nuclear reactor or a solar system. And these kinds of systems are used today, as I'll show in the next slide. There's also a single tank version of this where you have a tank with hot fluid on top and cold fluid on the bottom. Now, hot and cold nitrate salt storage is now used in thermal storage systems, in solar power systems. This happens to be an example of a solar power tower. I think it's out in Arizona, or Nevada somewhere, but as you can see, they're reasonably large tanks of hot salt. One's a hot salt tank and one's a cold salt tank. And you can use this as a heat storage technology. And there are, of course, three classes of heat storage. You can store liquids, salts, oils, and sodium. Salts and oils are currently stored in solar power plants. Pure liquid storage is nice, it's neat, but it's sometimes expensive. And people are looking for cheaper storage materials to put inside these big tanks. And so you can put insensible heat to be the primary heat storage media and flow the hot fluid in or out. People are looking at things like iron, steel, because it's $500 a ton, inorganic, sand, rock, and a variety of other materials. And there are what they call phase change materials that freeze and thaw. Lots of options. The catch is nobody's systematically sorted through these options. Some are well developed, some are not well developed. So we have a lot of options, but it's not a good understanding of what is practical on a large industrial scale. A lot of things you don't learn about until you do them at scale, and then you discover what the problem really is. Phase change materials, classic example. There's a thermal expansion and contraction upon freezing and thawing. Is that easy to handle? Is it difficult to handle? Many cases in the lab, the answer is yes. Large scale, to be determined. Important item to be noted about heat storage in general. You can add electricity input to the thermal heat storage. If you have a heat storage system and somebody is trying to sell you to have electricity at these incredibly low rates in the middle of the day, and you have a salt storage system, there's no reason why you can't buy some of that when electricity prices are low and put it into storage. So if you have a salt storage tank at a solar facility or a nuclear facility, and you normally think I'm providing the heat by the solar plant or I'm providing the heat by the nuclear plant, that's fine. But if somebody's going to start selling you electricity at this price, may I suggest, in addition to taking your heat from your nuclear or solar unit and putting it into storage, perhaps you should just buy electricity off the grid and store it and take advantage of the storage system you have. And then, of course, you've got more heat into storage, and you put that heat into your power plant when the prices are high. And that's true of any of these storage technologies. If you've got a storage technology that's getting most of its heat from a thermal source, if somebody out there is doing this kind of stupidity, actually it's good economic sense, let's buy the electricity and turn it into heat. It's an economic argument. It's not, it's for theoretician in thermodynamics, they sort of, wasting energy, creating entropy. Let's take a look at the second class of heat storage. These are heat storage technologies buried in the power cycle. And I'm going to take a look at two. This happens to be of the steam cycle. We had a workshop this summer at MIT that went into it. You can get a copy off the grid. This happens to be heat storage coupled to steam cycles in nuclear plants, but essentially the same technologies apply if you happen to have a solar plant. And there are 6 technologies from steam accumulators, sensible heat storage, cryogenic air, packed beds, geothermal energy storage, and hot rock. I'm not going to go through all of those. I could have a 2-hour talk on 6 storage options. I will mention that 2 of these technologies are commercially available for heat storage associated with the steam cycle. One is the steam accumulator, and the second is sensible heat storage. What's a steam accumulator? We have a big tank of cold water. When we have excess energy in our power production system, excess steam, we use the steam to heat the water up to its saturation point. Just pour in the steam, heat the water up to its boiling point. Steam discharge, we want extra power, we open the valve, we flash steam, and the steam goes to the turbine or the feed water heaters within the steam cycle. We store the heat as hot water because it takes less than 1/3 of the volume of storing hot, compressed steam. Strictly economics. Well, what's the technology? First one of these steam accumulators was built in 1929 in Berlin. 50 megawatt turbine, 67 megawatt hours of tanks. You can see the finest of 1929 technology. It's not exactly a new technology. Or if you want one current variant, this happens to be a solar plant in South Africa that's coming online last year. I haven't checked to see if it's online yet or whether they had construction delays. And here's their steam accumulators. So that technology, find the vendor you like, send him a check, and he'll build a plant for you. The other option is storing heat in a low pressure liquid or solid. You can store it as a nitrate salt, you can store it as an oil, you can do lots of storage techniques. This happens to be the Nevada 1 system where they store oil as the heat storage fluid. In this case, the reason they use oil is that they have this solar collector farm where oil is the heat transfer fluid. So the sun shines down, collects, heats up oil, and the oil goes into this piping network that's actually the storage system. I'm still not quite sure why they have this convoluted storage system of pipes, very big pipes rather than tanks. I'm not quite sure. I think what they wanted is a system, a flow-through system, and that guarantees it, but it's sort of a strange way of, from my perspective, of doing things. In the nuclear game, Westinghouse is looking at sensible heat storage. Steam heats oil. Oil is then used to heat concrete. What they're talking about is storage modules that have concrete plates in them. And you run the hot oil in, heat the concrete to high temperatures, and the concrete, of course, is the heat storage media. Why do you want to do that? The answer is concrete is cheaper than heat transfer oil. I know heat transfer oil sounds cheap by the tank car. Concrete is cheaper. It's all about cost. It's not very exciting, but the winner or winners are going to be the people who are most innovative at driving down the cost, finding low-cost materials and figuring out how to do them in a highly engineered system for heat storage at the lowest possible cost. Now I'm going to turn to the last general subject, but by far the most complicated subject, but where I think the future is going. But it may not show up for 20 years. And it's some kinds of systems that are in the research stage. These others have been deployed in various levels. These are in the research stage. And I'm going to discuss gas turbines with Firebrick resistance heated energy storage. And the goal, of course, is to buy and sell electricity. And what we're talking about here is a combined cycle plant with fires. This is a midterm option. Here we have our conventional gas turbine. We compress air, heat it with natural gas, goes through a turbine, and goes through a heat recovery steam generator up the stack. There are dozens of these sitting around California today. I took Route 166 on the way from the airport to to Santa Barbara, headed to a slight detour thanks to a little road problem you happen to have. And I went by at least 2 gas turbine plants that were sitting out there. If you know what they look like, you know, you have an absolutely unique profile. You can spot them at a mile. However, California's got this cheap electricity. So the next obvious item is, when you have cheap electricity, what about heating up Firebrick in a pressure vessel? Let's say to the same temperature, 1600 C or 1400 C or 1200 C, whatever your gas turbine is, when we have low electricity prices, and then take our compressed air, run it through the Firebrick, and replace some or all of the natural gas, go to the turbine, into the heat recovery system. In effect, high temperature heat storage in the Firebrick. Now, why do we want to store heat in Firebrick versus some other materials? We've been looking at a turbine that's been around 15 years, the GE F7B gas turbine, because all the data is out on it. That turbine has an inlet temperature of 1065 Celsius. In comparison, Mitsubishi has a new turbine on the test stands for their next generation power system, where the peak inlet temperature of the turbine is 1600 Celsius. As a point of comparison, that is the melting point of iron. By the way, the Air Force has gas turbines that run over 1750 Celsius. Iron flows like a highly fluid liquid at 1750 Celsius. Now, there's a difference, by the way, between Air Force gas turbines on fighters and utility turbines. In the Air Force, combat turbine gets 1,000 hours. Send a congratulatory note to the turbine manufacturer. 1,000 hours, fantastic. 1,000 hours, I need maintenance on a utility turbine, or 10,000 hours on a utility turbine. Send a note to the manufacturer, we're going to sue the bastard. We should be able to go at least 40,000 hours before an overhaul. For point of view. So as a consequence, utility turbines always run a couple hundred C lower than the US Air Force. Now, but well, you can see where we're heading. We're heading to, in a couple of years, certainly within 6 or 7 years, to 1600 C. Now, if you think about a heat storage media, what heat storage media do you know of that can go at 1600 C? Any candidates here? Got platinum. Sounds a little expensive. We got tungsten. That's pretty expensive also. And then we got Firebrick at dollars per ton. And so if you're talking about storing high temperature heat, you have only one storage option: Firebrick. Hittites are quite familiar with it. The other factor is you can't have a heat exchanger in the system, because the problem is, what do you make that heat exchanger out of? Unless you want platinum or palladium or tungsten heat exchangers, you're out of luck. So if you're going to talk about high temperature heat storage above 1,000 C, whether you like it or not, you're stuck with Firebrick. I know it sounds a little primitive, but that's the real world. So there's an engineering reason why I mentioned Firebrick, and it has to do nothing with the new technology, old technology. It's a materials problem. It's a fundamental materials problem. And of course, the game here is buy low to have heat available when the price is high. Now, we would expect when now developing these systems is non-trivial. Your electrical heating systems, you're putting the Firebrick in a pressure vessel, so this is a non-trivial task. But my suspicion, and I suspect that we'll have far better economics for the following reason. If we buy this system, which is 60% efficiency now and will probably be around 65% efficiency given advances in gas turbines within a decade, we can store energy. But if we run out of stored heat, we can pour in the natural gas, we can pour in biofuels, we can pour in hydrogen, and always generate electricity. Guaranteed capacity. You don't have a blackout because you ran out of storage capacity. If you buy batteries, and you buy a 2-hour battery or a 4-hour battery and you have 5 hours where you need electricity, it's time for a blackout. So if you're a utility and you're a great believer in batteries, you also have to buy the gas turbine to guarantee the capacity, to guarantee you can produce electricity if you have a couple of days of no sunlight or no wind. And so when you start thinking about it from a systems point of view, you suddenly realize, this is going to be a tough job to develop. On the other hand, guess what, guys? I'm stuck buying the gas turbine no matter what. So if you've already paid, you're already committed to this machine, whether you hate it or like it, doesn't make any difference, you're stuck with it. Then suddenly these systems, even though they may not have the same round-trip efficiency as a battery, start looking very attractive. Last, I'd like to talk about the longer-term future, 20, 25 years out, and that's high-temperature reactors with Brayton combined cycles, where I think we're ultimately going in the nuclear game. And the goal here is we have a nuclear reactor, high-temperature nuclear reactor, hooked to a gas turbine, producing peak power using natural gas or hydrogen to produce variable electricity to the grid. This technology would apply to a fluoride salt-cooled reactor, solid fuel, liquid salt, a molten salt reactor with fuel dissolved in the salt, salt-cooled fusion if we have any fusion fans in the audience, or a high-temperature solar power tower. And for all of these applications, people are beginning to think about these power cycles, because what's required if you're hooking to a gas turbine is you need to be in the 600 to 700 C range temperature. Doesn't matter what the heat source is, 600 to 700 C. 800 would be nicer, but this is where we're going from. And the reason you have to be so high happens to do with the gas turbine cycle. The front-end gas turbine of a modern industrial gas turbine is going to get you near 400 C by the time it comes out of that front-end compressor. And since you're at 400 C, if you're going to add heat to that 400 C hot air, you've got to be substantially warmer than 400 C. This is all driven by gas turbine requirements. Let me show you the cycle. The same cycle would be with solar. Normal baseload operation, filter air, we compress air, we heat the air in a heat exchanger. With a reactor or a solar system, goes through turbine 1, heat in the second heat exchanger, goes through turbine 2, run it through a heat recovery steam generator, producing more steam for electricity or heat to industry, and up the stack. Very close to existing gas turbine plants. This system, if you have 600 to 700 C, it will be 42, 43, 44% efficient. Important point here. What limits the temperature of this system if it's hooked to a nuclear reactor? And the answer is, or a solar system for that matter, the answer is the material limits of that heat exchanger. Once you get above 700 C, getting a reliable, cheap, long-lived heat exchanger much above 700 C is a real challenge. Reliable and cheap. Now, here you've got this 700 C exit temperature for the compressed air. And here you've got a gas turbine that looks at 700 C heat and looks and says, gee, what a cold day I have. It's like freezing in the Antarctic. This is a turbine where we can design to 1600 C. So you got 700 C heat, it works, but the turbine frozen solid. So we have the little option of adding natural gas or hydrogen or stored heat at this point in time and raise the temperature of the gas going into the gas turbine. So what? Here's our baseload electricity. Let's assume 100 megawatts. We heat the air up to 670 Celsius, 42% efficient. Let's have a topping cycle. Could be fires, could be natural gas or hydrogen. And let's say we heat it up to 1065 C. That's a GE F7V gas turbine. We generate another 142 megawatts at 66% efficiency. What's important about that number? A top-of-the-line gas turbine today, standalone gas turbine, has an efficiency of 61%. The incremental heat-to-electricity efficiency is 66% because it is something called a thermodynamic topping cycle, where we're adding heat above low temperature 670 C compressed air. Key point to remember here, that's low temperature. That very high efficiency means we consume less natural gas than a standalone gas plant. And in economic terms, what that means is if we have this plant and you have a standalone gas plant sitting down the road and we're competing, we make out like a bandit because we're burning less gas for more electricity. And it boosts your revenue, in this case, by 50 to 100%, depending upon which market you're in, Texas or California. With a modern the Mitsubishi gas turbine, if you get up to 1600 C, this efficiency is going to end up somewhere around 75%. It's the extraordinary implications of a thermodynamic topping cycle above low temperature heat, 600-700 C, generated by nuclear or solar. Welcome to the miracles of thermodynamics. And of course, what the game here is we want to use the low price fuel, be it uranium or solar, to get the initial heating, and use the higher price fuel for the higher temperature environment. Now, so what that implies is we put fires in here and away we go. We buy electricity cheap and we convert it to incrementally heat efficiency. As I say, today it would be in the 66, 67%. By 2000, in another 20 years, you're probably going to be over 75% if Mitsubishi, GE, and Siemens projections on turbine capabilities are possible. So you're talking about electricity to heat to electricity efficiency that's going to be over 70%. Now you're in the range of round-trip efficiency equivalent to a hydro plant. And you're not quite up to batteries, but you're getting up there pretty close. And because I can dump in natural gas, I have guaranteed capacity, or hydrogen, or any other fuel, or biofuels. Doesn't matter if the sun doesn't shine. It doesn't matter if I don't have cheap electricity for 2 weeks. I can guarantee electricity delivery to the grid. Now, the operation strategy, buy prices, for this is for fires. Electricity to fires when low prices, you take all the electricity from the plant, run it into fires. You don't want to sell electricity if it's cheap. Electricity from the grid. So when you're in this condition, you buy electricity from the grid and you don't sell it to the grid. When it's high priced, you could do peak power. You've got the same capability as batteries and pump storage. And ultimately, the electricity heat to electricity efficiencies are near 75%. Now, I should mention something about these Brayton power cycles. Until 15 years ago, the gas turbines were not good enough to pull this stunt off. In the 1960s, gas turbine efficiency was 15%. Loser. It's the advances in gas turbine technology, incredible investments over 50 years, that about 15 years ago, with the GE F7B gas turbine, was the first turbine that was good enough to put in these topping cycles. Before that, the gas turbine wasn't ready. So this is a case of where a technology we're looking at today was waiting in time for the advances in gas turbines. And that's true of a lot of situations where a technology comes along in some other field and it opens up new opportunities elsewhere. This is not unique to energy. It's a very common phenomenon. Last, I'm going to briefly mention hybrid systems, co-produce electricity or one or more electric products. Been a lot of discussion of this. I want to operate the reactor at full capacity with variable electricity to the grid. You have the option of producing electricity in a secondary product. Typically, people look at something like hydrogen. If you're producing a secondary product, you have to have a large demand for that, so you can absorb a lot of electricity, and you have to have low capital costs for the process, and you have to have the capability to ramp up and down quickly. Now, heat storage can substantially improve the economics. Heat to hybrid systems bypasses the expensive heat to electricity systems, and there's a potential for low-cost energy, the buy low, sell high. It's a separate set of coupled options, equally complicated as everything else I've discussed today. And again, we've only begun to explore this. And that's because until a couple of years ago, we had a very simple system. The electricity prices were controlled by the fossil fuel combustion. And when the demand went down, you shut off the fossil plant. And so the price went down to some minimum. It didn't go below that because everybody flipped off the switches. It's only when you add these high capital cost, low operating cost technologies, wind, solar, and nuclear, in large quantities, that you change the market. And that's what makes the difference. Well, some conclusions. And again, the most important one is electricity markets are changing. In a low carbon world, we require dispatchable electricity. The world is transitioning from low capital cost to high operating cost, high capital cost, low operating cost energy systems. Second, energy storage is cheaper than work storage. Lots of heat storage technologies with different capabilities. I mentioned fires specifically because it's a very low cost technology that may set a minimum price of electricity close to that of natural gas. But there are lots of other options: heat storage between the heat source and the power systems, heat storage in the steam cycle, and heat storage in a gas turbine cycle. With that, I'll stop and open up for any questions you might have about these power cycles or the heat storage. By the way, let me mention, there is on some website somewhere, maybe somebody knows where, the long version of this talk. Well, this is a consolidated version, so if you want gory details.
It will be posted on the IEE website once we get the video.
Okay. Important point to note. Yes?
Thank you. Really nice talk. So can you just compare in terms of volume and weight the fires and batteries, and how big of a problem would be thermal isolation for larger scale fires storage?
Fires with 1,000-degree variation in temperature is about a megawatt per cubic meter, roughly speaking, which is pretty good. It turns out that for most fires applications, not all, but most, that thermal heat losses are very close to zero. That needs a little explanation. What are we doing with fires? Heat up Firebrick, and we take cold air to produce hot air. It's used for something. We can design fires with a Firebrick, and we can have two layers of insulation, an inner layer of insulation and then an outer layer of insulation that has a couple of air channels flowing through it. And we take our cold air going from the outside through the outer layer of insulation, cooling it down, and run it into fires. And so when we're running fires, discharging fires, we're cooling the outer layer of insulation. So when we go into the charging mode, what you got is the inner insulation layer and then the outer insulation layer, which is just cold. And so it essentially acts as a heat absorber and as well as an insulator. And so we have this strange dynamic insulation system where we have an odd situation where our heat losses can be very, very close to zero because the input is cold air and the output is hot air. You know, and that's because that's what couples to everything. It's a very unique system, and otherwise you'd normally worry about these things.
Can you talk a little bit about how it scales down? Because people will talk about substation storage for the electricity grid, which are a few megawatt hours, relatively small. This probably doesn't keep a double-digit dollars per kilowatt hour at small scale, does it?
It depends what your application. In the home heating application, if you go through the catalogs for these home heater things, those are in the $15 a kilowatt hour small scale. If you're making electricity, the issue here is what's the cost of the power conversion system. Fires will scale down, not too badly, but the power conversion system may not. That's the real issue. If you can develop a very efficient Stirling engine, maybe you can make a smaller system. I don't know.
On the scale up, then, you're talking about 1,500 degree fire brick, but
Yes.
compressed air.
That's right.
on top of it. That pressure vessel, if it's big, which you require for a high service to volume or low service to volume ratio, that's going to be a pressure vessel that's pretty expensive to keep at 1,500 degrees. I don't care what the insulation is. That's a massive pressure vessel.
Yes, it's in the backup slides. Turns out that some other people by the name of, General Electric have been working on this problem. They've been, and they have a project that's now on hold because of changes in price structures in Germany. This is a project with RWK, the German utility, where they're looking at adiabatic compressed air storage. And the adiabatic compressed air storage, what you do is you take air, you compress it, actually to about 600 C and 70 bar, run it through a recuperator in a pressure vessel and inject the compressed air underground into a salt cavern for compressed air storage. Now, the compressed air goes through a recuperator because you can't have 600 C hot air down in your salt, or your salt cavern begins to fall apart because of the high temperatures. To discharge this storage device, the compressed air comes up, goes through the brick recuperator, gets reheated, and heads out to the gas turbine for peak power production. And they have been looking very carefully at how you build a pressure vessel with a recuperator in it at scale. And they've built about a 1 meter thick cross section of this pre-stressed concrete vessel in the lab of what this thing would look like. And the numbers look pretty good. They haven't gone through a lot of the details. The problem is that the storage market, because of the market rules in Germany, are so screwed up that nobody can afford to put in storage in the system. They're actually decommissioning some pumped hydro facilities. It's a crazy market. But the technology is there, and I think the costs will be reasonable for these kinds of systems. But you know what you got to do is you build it. You know, at the end of the day, you got to build it. But the efficiency will be much better on a big gas turbine. I mean, these are remarkably cheap machines.
Thanks very much for your talk. I learned a lot from it. As you indicate in that fourth line of your conclusions, you don't have a lot of enthusiasm for electricity storage.
For utility operations, not for hybrid cars where you've got where you have a real weight limit.
Right, but so my question is, you know, there's quite a bit of interest among the utilities, at least as I understand it, in California, for battery storage, and even our campus actually is looking into this possibility of, you know, within a restricted grid, doing some storage so that we could capture some of the solar electricity at midday, or also for just backup purposes. But what I took from your talk is that might be a misguided approach. And I just wondered if there's any instances where you think that is the right approach using batteries.
First place, people want to have storage. You want something you can have delivered in 90 days. And if 90-day delivery is on your list of things to do, your option space is really small.
Right.
And you know, what they're doing is they're grabbing the technology over there because it's the one you can do. So what I'm talking about is, you know, when the dust settles and people have time to bring on other technologies. The only place, there are two places where batteries look good on the electric grid, but both of them involve very small amounts of capacity. One is for frequency regulation. And I think on the PJM grid, which happens to include New Jersey and New York, they ended up with a couple hundred megawatt hours of storage for frequency regulation. So the market is, well, gee, it's a really nice thing to control the frequency well, but it's a zilch market. The other place where the economics look potentially favorable is if you have a transmission grid constraint and it's going to cost you a bundle to upgrade a particular segment of the transmission grid. And in some cases, it will be cheaper to put in battery storage so that you don't have to upgrade that chunk of the grid and pour the excess electricity over in the middle of the night when there's low demand to meet peak demand in the day. But those are the only two cases where I've seen one can make a credible economic case with batteries.
Santa Barbara's in that latter case, where we're constrained by
The grid.
transmission lines.
Yep, that can put you in it. For general storage, the numbers that have been run by various groups look really depressing.
And that's true even if you can get the price down to that
Yes,
$50
yes,
kilowatt
yes.
hour.
Yeah, and it comes down to the raw cost of the materials going into lithium-ion batteries. But remember, if you want to do something today, you want a flatbed truck to come in and deliver in 90 days, you have to choose the technology you have today. And this change in electric market has only happened in the last couple of years. And so these alternatives have not had time to develop. Whereas lithium-ion batteries have had 30 years of development. You know, first they got developed because Sony had this PlayStation, you know, the portable PlayStation and all this other stuff. I don't know if any of you are aware of the history of lithium batteries. They've been around forever, since I think, what, the 20s or 30s, somewhere in that time frame. Didn't go anywhere because everybody figured it's $1 billion to figure out how to make them at scale. And then there was this company called Sony that made all these portable electronics, and where the problem was the battery, and somebody said, lithium-ion battery, that'd solve our problem. billion-dollar development program. Gee, that's chump change compared to the money we're making in electronics. Go do it. And that's because they had a market. They got a 30, 40-year head start, and then they got into hybrid vehicles. The catch is these other technologies had to wait. Had to wait until the market existed. Sony created the market for lithium-ion batteries. Until 2 years ago, there was not a market for large-scale heat storage in the United States. So this is a time phase problem. So the question is time.
But now steam turbine cycles work. You can go buy one on a truck in
That's right.
90 days.
Oh yes, you could do that.
You would take a picture, it wouldn't be as elegant as a gas
Well,
turbine.
our friends at Siemens are doing a version of this with hot rock,
Yeah, I mean,
and they're going to heat the hot rock to 600 Celsius. And they have a prototype they plan to build in the next 18 months with a packaged steam boiler hooked to a dumb turbine to be sent out on some guy's wind farm. And that's because of the German, that's a transmission grid issue again. But they're actually, they plan to have a prototype, I think, up by 2020.
if it's a factor of 10 cheaper than batteries, then you can take a hit in the
That's right.
efficiency.
Well, the Siemens is actually going to plan to build that system, 600, 700C. Hot rock rather than Firebrick. Hot rock comes out a little bit cheaper, and if you don't need to go to high temperature, crushed granite happens to be cheaper than Firebrick. Bigger issue if you're going to high temperatures. Yes?
I have two questions. Number one is, when you talk about hydro storage, what kind of round-trip efficiency you are talking about? And number two is, even if it is like, let's say, a megawatt or a 10 megawatt storage, megawatt hour storage system, can you address in terms of cost, installed cost per kilowatt hour?
Okay, well, first, hydro pump storage typically are in the 70 to 80%, which is very, very site dependent. There's some a little bit higher, 82, 83%, but the low ones are 70, and that depends on the elevation difference and what equipment they are. For the heat storage costs, we're talking about $15 a kilowatt hour for storage or less. And in terms of electricity cost, you know, your goal is to add a penny or 2 pennies per kilowatt hour because of the storage system. That's for thermal systems versus 10 cents or 20 cents or 30 cents for the battery systems. The one item I will warn you about economics on utilities is you have to think about the entire system. It's not just the storage. You've got to have assured capacity. People do not like blackouts. I mean, in Santa Barbara, you can tolerate a blackout. Where I grew up in the upper Midwest, where it goes down to minus 40 C, blackouts are viewed as time to replace the utility CEO, which is exactly what they do, by the way. If you have I grew up in a hometown that had 2 power outages in 30 years. This long one was 15 minutes. They had zero tolerance for long outages. Yeah, I should mention a town that has a big milk industry, milk and cheese, and you don't think about it, but you can't have long outages. If you're storing milk, it goes sour. More importantly, they have these milking machines for animals, and if you don't milk a cow regularly, really regularly, what happens is it goes out of production, and the only way to get production back up is run through another pregnancy. And you start thinking about 6 to 8 months of feed for a 1,100-pound animal because somebody didn't provide power for 24 hours, you understand what the requirement is for electricity demand. The answer is you cannot have long outages. It's absolutely unacceptable economically. The same, by the way, is true of certain kinds of chemical industries and certain types of electronic industries which have an equally zero tolerance policy for any lengthy blackout and a lot of backup equipment to guarantee it. You know, reliability depends on what the local industry is or if there's severe severe health effects like people freezing in the dark. In Santa Barbara here, power goes out. Oh, gee, I'm going to have to go out and enjoy that beautiful weather on the beach. Really a tragic event. I shouldn't put it that way, should I? But I've noticed you really have some, I understand why your recruiting strategy for professors from the Northeast is highly successful. I left it during a snowstorm, by the way.
Both of these technologies might be a little farther out on the horizon in terms of deployability, but you compare it to like battery technology or to like potential energy storage. Do you see any potential for either supercapacitors or kinetic energy storage?
Flywheels. Both of those are tend to be for people who need very good, tight frequency controls. So there'll be a specialty market. There's no question about it. It'll be for server farms, things like that. But that's not general bulk utility. If server farms it's a big market, but it's a really specialized market where they don't want to miss a cycle. And so you're in a different world. So there are all sorts of specialty markets. And yes, in those applications, yes. But not for general purpose heavy duty grid applications. The difference is when grid applications on a large scale, low carbon world, we're talking about hundreds of gigawatt years of storage, really big quantities. Versus, if it's gigawatt hours and gigawatt years, you're talking grid, otherwise you're talking megawatt hours. But there's somebody can make a bundle of money in these specialty markets. Just go talk to Google, who owns more server farms, or no, I guess it's Amazon that actually owns more server farms than anybody else, followed by Google.